Welcome. In this video, I'm going to go over the solutions I believe are correct for the Paper 2 SL Chemistry exam given in May of 2017. The first question starts out and says the rate of the acid-catalyzed iodination of propanol can be followed by measuring how the concentration of iodine changes with time. So it suggests how the change of iodine concentration could be followed. So when you look at this, you might be tempted to look at a pH indicator because the H plus being produced, but it says it's acid catalyzed. So a more appropriate choice for iodine concentration would be starch. Starch turns blue in the presence of iodine. And I don't know if IB expects you to explain it at all. It's only 1 mark, so I think just realizing that starch is your best indicator here would net you the 1 mark. Part 2 said a student produced these results with 0.15 molar H plus acid, propanol and acid were in excess, and iodine was the limiting reactant. So I've got my concentration of iodine here. I've got my time. So using the rate equation of change in concentration over time should yield my reaction rate. So I'm just going to go ahead and use the extremes. So my rise changes from 0.80, or 0.8 I guess more correctly, and I'm going to estimate that to be, I guess I can estimate to 0.80, and I'm going to estimate my n to be 0.35. My change in time is 0 to 60, although we don't express rates as a negative. But this gives me a rate of 7.5 times 10 to the minus third, and then make sure you include a label, which would be moles per decimeter cubed per second, just like you get, so you can see the minus 1 there, when you combine the units given here. Part B, the student then carried out the experiment at other acid concentrations with all other conditions remaining the same. And remember, we know this value right here, 0.15, we came up with 0.0075, which seems to fit the trend here. And state and explain the relationship. As concentration increases, so does rate. And the other mark here is for explaining it, and that's because there's more H plus available to collide with. In Part B, it says titanium exists as several isotopes. The mass spectrum of a sample of titanium gave the following data. So you can see I've shown my weighted average here. I like to take 46. I like to take each mass number times the percentage given and then just divide by 100 at the end. Then I don't have to convert each one, and I don't have to worry about making mistakes, especially when the percentages fall below 1%. And to 2 decimal places, I actually get 47.92. And then my label needs to be AMU since it was said to be relative atomic mass. Part C, state the number of protons, neutrons, and electrons in the titanium-48 atom. Well, the protons is going to be 22, and the electrons 22, since that's the atomic number. And then 48 minus 22 would give me 26 neutrons. So pretty gentle beginning with 1 and 2. Part C, state the full electron configuration for the titanium plus 2 ion. And again, this is titanium-48, which is irrelevant on the configuration. So the full configuration would be 1s2, 2s2, 2p6, 3s2, and now it gets a little messy because it'd be 3p6, and typically if I hadn't had the plus 2, if I hadn't lost 2 electrons, it would be 4s2, 3d2. So the question is which 2 electrons get pulled off first. It is the 4s2. So this is my complete configuration, and I should move the 3d2 over there so it looks like it's part of the same configuration. But that would be the correct way to express the Ti 2+ ion. Part 2, explain why an aluminum titanium alloy is harder than pure aluminum. Because you're mixing, aluminum's a soft metal. So when mixed with the harder titanium, it gains strength, makes it a harder metal. That's the whole point of alloys, is try and enhance positive characteristics. Letter E, part 1, state the type of bonding in potassium chloride which melts at 1043. I would expect this to be ionic, and the high melting point confirms that. Number 2, though, a chloride of titanium, TiCl4, melts at 248 Kelvin, suggests why the melting point is so much lower. Well, this suggests that it's not ionic, that this must be a covalent bond. And in fact, if you look at your data booklet, you see that you're looking at electronegativity difference of 3.2 and 1.5, which is 1.7, and that's right about where the difference, the boundary is between being considered covalent and ionic. So this low melting point would suggest that this is a covalent molecular structure. TiCl4 reacts with water, and the resulting titanium 4 oxide can be used as a smokescreen, formulating an equation. Well, TiCl4 plus water, and I know that I'm getting titanium 4, so TiO2. That means this is just a replacement reaction giving me HCl, and then to balance, I would need a 4 here and a 2 in front of my water. Question number 2, part 2, says, suggest one disadvantage of using the smoke in an enclosed place. And what they're getting at is that anytime you have smoke indoors, it's a pollutant. Oh, let me give a pollutant, and that means it crowds out the oxygen that we need. And especially if I have titanium oxide, I would assume that's going to be more dense than oxygen, so it's going to tend to push the oxygen toward the ceiling and out of reach for many of us as we're breathing. Number 3, vanadium, another transition metal, has a number of different oxidation states. Determine the oxidation state of vanadium in each of the following species. So V2O5, I have 2 vanadium that when added to the 5 oxygen at a -2 charge each should have a total charge of 0. So if this is -10 and this has to provide a +10, then I can see that each vanadium must be a +5. On the second one, I have a single vanadium that combined with 1 oxygen at a -2 should give a +2 overall charge. So that leads me to realize it's a +4 in this case. And then part B, here's a redox equation for you, and it's actually a pretty easy one. Formulate an equation for the reaction between VO2 plus and V2 plus to form V3+. So you just need the equation in there at the end of it all. But what I'm going to do is go ahead and look at the 2 half reactions. I've got VO2 plus becoming V3+. So I'm going to need an H2O over here, which means I'm going to need 2H plus over here. And if I look, my difference in charge then is, actually my 1 electron goes on the other side, is, plus 1 electron on this side. And then my V2 plus becoming V3 plus. And that makes sense because remember, vanadium's a +4 here, and it's being reduced to a +3. And then V2 plus to V3 plus, I don't need to add any oxygen, so then I don't need to add hydrogen. I just need the 1 electron on this side. So when I add this up, I have 2H plus, I have my VO2 plus, I have V2 plus, and then I end up with 2 V3 plus ions. I'm getting 1 from reduction and 1 from oxidation. My electrons cancel out as they should, and I have an H2O. So that's the equation they're looking for on part B. So that's the first 3 questions from paper 2 of 2017's SL Chem exam. I'm going to make a second video to go through questions 4 and 5 since they get a little lengthier and I don't want this one video to extend too long.